So the last few minutes, maybe I'll just go very quickly on the adjoint of implicit functions. The idea is the similar. If I have j as a function of u, and my u satisfies f of u s equal to 0, I can add this with u hat times f of u and s, right? And my delta j would be partial j partial u times delta u plus u hat times partial f partial u times delta u plus partial f partial s times delta s. Here, what do we want to eliminate again? What do we want to eliminate what do we want to avoid having to solve for different delta s's? Yeah, or both of these delta u terms. And how can we, what equation does u hat has to satisfy in order to cancel these terms? I want to cancel these terms for whatever delta u that could possibly arise from the perturbation in S, right? So what equation should I satisfy? You had times this df du, right? These two has to be the minus dj du, right? So basically the way to derive this is to pull delta u out. So dj du plus u hat times df du times d delta u. So these are the two terms that contains delta u, and then the term that doesn't contain delta u, we don't have to worry about it, right? So we want to set this to 0 because we don't know what delta u is. We should be able to allow arbitrary delta s, therefore arbitrary delta u. So with that, this is the equation we end up solving, and once we solve that equation, the delta u can be just the u hat df ds times delta s. Okay, so all of these are ways to get us how does the objective function change as we change an arbitrary delta s. The answer to this question gives us the gradient, right? So if you are able to evaluate the change in the objective function with respect to every change in s, then you can perturb, you can set delta s equal to 1, like epsilon 0, 0, 0. You can then set another delta s equal to 0, epsilon 0, etc. You can do this for n times n being the dimension in s. Then you get the partial derivative of j with respect to every dimension in s. You get the gradient. And that's the gradient we use to drive optimization algorithms. You can use a steepest descent, and the steepest descent is actually what the machine learning community has been using pretty successfully. And you can also use a Newton type of method. If you don't have the second order derivative, you can use the so-called quasi-Newton method. And the quasi-Newton method only uses gradients. By computing the gradients at multiple s's, it tries to construct an approximation to the Hessing and use that Hessing to drive optimization further. You can also compute derivative of not the objective function but the constraints, right? And the derivative of the constraints is going to be very useful for optimization also. So this concludes our discussion of how do we compute the gradients for complex computational models. And that's useful in doing optimization and also other things. I'll see you on Friday to discuss statistical models which you're going to see actually use some of the optimization ideas to find the statistical parameters that best fits the data. All right, I'll see you Friday.